Welcome to Lecture 33, in which we continue our discussion of the Deutsch-Jozsa algorithm. Last time we learned about the preliminaries and we understood what this algorithm is supposed to do. Briefly, it allows Alice to send Bob hopefully just one query, and from this one query of the use of f unitary transformation, she will be able to determine whether the function f, which is a function of n binary variables, is a constant function or is a balanced function. And remember that balanced means that for half of the possible inputs to f, it has a value of 0, and for the other half, it has a value of 1. Of course, constant means it's either always 0, or it could also mean that it's always 1. And so we're guaranteed that Bob's function f is one of these. It's either a constant function or a balanced function. And we found out that if Alice wants to try to determine this in a classical fashion, it could take her as many as 2 to the n minus 1 plus 1 different queries. But we're hoping to find a quantum computing approach that will require only one query. And so this is the way that it will go. Alice starts, and by the way, this algorithm is described in your book, and it's also, in fact, it's in pretty much any book of quantum computing, but I'll be using the notation and some of the ideas, just as I was before, from the Nielsen and Chuang book that we'll be using next semester. So Alice starts with a state that we will label as C0, and it's given by the following. So in other words, it is a state, an n plus 1 qubit state. The first n qubits are all zeros, and the last qubit is 1. And the first n qubits, this is the n qubit query register, and this last 1 qubit is in what's referred to as the answer register. So Alice starts with that, and then she applies H to each qubit. To obtain C1. So what is C1? Well, C1 will be, remember that when we obtain H to each qubit, the one shorthand way of writing that is W. So we would have W, and just to make sure you understand, that's H tensor product H tensor product H dot 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 tensor product H. We have that n times. So we have W acting on 0, superscript m, superscript n, which means, again, this is just the n qubit state consisting of all zeros. And then we also have h acting on that final qubit of 1. And again, now this is just applying h to every qubit of C0. We're going to call the answer C1, and you can see that that's exactly what we've done here. We've applied n h's to this first part, and then we've applied one more h to the second part, which is the last qubit. Okay, so let's just keep the first part as it is for a moment. And now this the evaluation of the second part is very simple, because we know that the Hadamard gate acting on the 1 ket is simply going to be 0, minus 1 over square root of 2. We learned that long ago and have used it many times in our different problems. So now all that remains is to, in order to get C1, is to evaluate W acting on this state, which is consisting of n zeros. But we have already done that. Let's see, I believe that this was in lecture 31. Let's go back here and see. And indeed, here it is, right here, W acting on 0, where 0 is understood to be this state right here is supposed to be n zeros. That's 1 over the square root of capital N, and remember, capital N is 2 to the nth power. So it's 1 over the square root of 2 to the n times the summation of x equals 0 to n minus 1 of x. Remember, we're using this notation there where each one of these is an n qubit state, and what this summation really means is just a summation over all 2 to the n elements in the standard basis. So this is what we need for C1 here in our present lecture. So let's plug that in. We have 1 over the square root of 2 to the nth power, and then we have a summation over x. I'm going to write this in this way. X equals all, or let's just say maybe some, well, I guess this is maybe the clearest way. X is equal to any element of the standard basis, and then the summation sign indicates that we're going to sum over all of those. Okay, and we get here x. Now this part right here, this is W of the n qubit state consisting of all zeros, and then we need to bring down this part as well. So we get 0 minus 1 over the square root of 2. So this is the value for C1. And this is what Bob will operate on. So Bob operates on C1 with u sub f. And let's make sure that we understand exactly what's going on here. Now, as I say, what's happening here is that C sub 1 is what is going into the unitary transformation U sub f. And so the first n qubits, you need to remember again that x is any element of the standard basis, and maybe I should say for n qubit states. So x has n qubits, and 1 qubit will be entering into each one of these lines. And again, remember that we have a superposition here of all of the different possibilities. So and we're going to refer to each individual possibility is a different value of x, okay? And so then, of course, we will have similarly n qubits coming out. And if we call this x coming in, then this is also, we know that that does not get modified. We'll have x coming out. But on the last line, we will have, let's write this like this. So here's x, and here's x, and this part is y, which is the 0 minus 1 over square root of 2. And then we know that what we'll have down here is y exclusive or f of x. And again, to make sure, x is the first part, this is the first n qubits, y is the last qubit, qubit here, which is a superposition of 0 and zero minus 1 over square root of 2. So it's a superposition of 0 and 1. And this is what our output will be. Now let's figure out, we're going to call this C2. The input is C1, the output is C2. So let's now figure out what C2 will be. We have up here, this is what C1 will be. Now we want to figure out what will C2 be. Well, the first thing that we can say is easy. We know that the first n qubits of C2 will be identical to the first n qubits of C1, because that's the way that this works. Here you can see here's the x and here's x. So C2 is going to be, we'll have 1 over square root of 2 to the n, and then summation x equals any element of the standard basis for n qubit states, and then we will have x. It's going to the first n qubits will be matching the first n qubits over here on the output will match the first n qubits of the input, regardless of which one of the x's we're talking about. Remember, we're going to be looking at 2 to the n different x's. One consisting of all zeros, the next one consisting of all zeros except for a 1, and so on. all the way up until we get 2 to the n ones. And of course, remember, in each case, we're dividing by 1 over square root of 2 to the n. So all of them are normalized. But when we put them together. But the point here is that regardless of which one we input, this holds true. That the first n qubits of the output will match the first n qubits of the input. And so now the question is, what do we get for this last qubit of C2? In order to figure out what this last qubit is, this y exclusive or f of x, let's reason as follows. Okay, and I'll work over here in the margin. So we have that this last qubit, y, is given by 0 minus 1 over the square root of 2. And what we want to evaluate is this y exclusive or f of x. So since y has both a 0 and a 1 in it, we need to look at both of those. Okay, 0 exclusive for f of x will be equal to 0. Remember that x is, or a exclusive or b is a prime b or a b prime. So if we think of, let me write that down just in case anybody's rusty with it. A exclusive or b is equal to a b prime ORed with a prime b. So if we think of a as being equal to 0 and b as being f of x, then we see that this term on the right, since a is equal to 0, this term drops away, and a is equal to 0, so a prime would be 1, and 1 ended with b is b, so we just get b, which is f of x. On the other hand, if we have 1 exclusive or f of x, well, now we have 1 playing the role of a and f of x playing the role of b. And so in this case, is this second term that will disappear, because if a is equal to 1, then 1 prime is 0, and 0 ended with anything is 0. So this would drop out, and we'd have 1, a is equal to 1, so we would have 1 ended with b prime. B, remember, is f of x. So 1 ended with f prime, and 1 ended with anything is that thing itself. So we just get f prime of x. And therefore, the answer to our question that we've posed here of what is y exclusive or f of x, well, now we can answer it. Since y is equal to 0 minus 1 over the square root of 2, and since y exclusive or f of x is f of x, and, oh, and by the way, we need to put it like that, and likewise down here, and 1 exclusive or f of x is f prime of x, then what we get here is y exclusive or f of x is f of x minus f prime of x over the square root of 2. And I'll rewrite that down here. y exclusive or f of x is equal to, now of course that's only true for this particular y, but it's equal to f of x minus f prime of x over the square root of 2. Now let's think about that for a moment. F of x is a Boolean function, and so it can only have a value of 0 or 1. So either this is equal to 0 minus 1 over the square root of 2, or it's equal to 1 minus 0 over the square root of 2. So we can, another way of writing y exclusive or f of x is to say the following. It's negative 1 to the f of x power times 0 minus 1 over the square root of 2. And let's make sure now that these two expressions agree. Okay, if f of x is equal to 0, then this would be 0, f prime of x would be 1, and we would have 0 minus 1 over square root of 2. And if f of x is equal to 0, then negative 1 to the 0 power is 1, and so we did this formula down here indeed gives us 0 minus 1 over square root of 2. So in the case when f of x is equal to 0, these two expressions agree, and now we only have to check it in one more case, and that's in the case when f of x is equal to 1. Well, when f of x is equal to 1, this would be 1 minus 0 over the square root of 2. But when f of x is equal to 1, down here, we get negative 1 to the first power, which is negative of 0 minus 1 over square root of 2, and so it becomes 1 minus 0 over the square root of 2. So these two expressions here agree in both of the two possible cases, and it is the latter one that we will use here in this expression. So we will end up getting negative 1 to the f of x power times 0 minus 1 over the square root of 2. And that will be the output from the unitary transformation u sub f. Now, Bob will provide that to Alice. And how does Alice use this? To determine if f is constant or balanced. Well, first, she applies h to each of the first n qubits. Now we're going to call, let's see, actually let me change that just a bit to say to obtain C3. Okay, so we're going to give the name C3 to what Alice obtains after she acts on the first n qubits of C2, on each of them, she applies to each of them the Hadamard transformation. And so let's now try to see what results she will obtain. Now it turns out that this is still another calculation that we've already done. And let's see how this goes. Okay? We're going to have C3. Now again, C3 is going to be the result of applying H to each of the first n qubits of C2. Okay, so we'll get 1 over the square root of 2 to the n, and then we get summation over x equals any element of the standard basis for n qubit states, and we're going to apply h to each one of the qubits of x, which is then the same thing as w. Remember again, just as we set up here, w is equal to just h n times. So that's w of x. And then we just bring down everything else we have from C2. So we have -1 to the f of x power times 0 minus 1 over the square root of 2. But now let's investigate this w of x, and to do that, as I mentioned, we're going to look at a previous result we have obtained. This result was from lecture 32, and it is right here. X, here is an n qubit state, and so we're going to let w operate on x, and when we work through this, this is the result that we obtained, that w acting on any n qubit state x would be 1 over the square root of 2 to the n times the summation over, we have zn minus 1 could be 0 or 1, zn minus 2 could be 0 or 1, z1 could be 0 or 1, z0 could be 0 or 1, of -1 to the x dot z. Remember that x has n qubits and z has n qubits, so we understand what x dot z means, times zn minus 1, zn minus 2, z1, z0. That's what w operating on x gives. So let's use that result, and I'm going to use that result in what we're doing now in lecture 33, but I'm going to shorten the notation a little bit. Notice that all of these summations, we're letting each one of the qubits in Z, we're letting each one of those assume all the possible values. So what this means is that altogether, this state Z is also assuming, we're just going to shorten that and call it Z, just like up here, we're calling x, we're calling this xn minus 1, xn minus 2, x x1, x0, we're calling that x. Well, similarly, we're just going to call this z, and all these summations can be just summarized into one summation where Z can be any element of the standard basis for n-qubit states. Because if we let each one of these assume values of 0 and 1, then we get all of the possibilities. So coming back over here then to lecture 33, we get now the summation over Z equals any element of the standard basis. For n-qubit states. And we have -1 to the x dot z z. This summation right here, let's just make very clear, this summation right here, oh, and we also need, we need a 1 over 2 to the n, so let me put that in as well. 1 over square root of 2 to the n. So 1 over square root of 2 to the n. That summation right here, and again, this is from lecture 32, this summation right here is W acting on X. And now we just bring down the rest of what we have from this line. So we'll have -1 to the f of x power, and then 0 minus 1 over square root of 2. And now all of this can be written a bit more compactly in the following way. We can take this 1 over square root of 2 to the n outside of the summation and combine it with this one, and we have 1 over 2 to the n, because it's 1 over the square root of 2 to the n times 1 over square root of 2 to the n, so it's just 1 over 2 to the n. And then we have summation over x equals any element of the standard basis for n-qubit states. And the summation Z is any element of the standard basis for n-qubit states. And then we'll have -1 to the x dot z plus f of x. That comes from combining, of course, this -1 to the x dot z with -1 to the f of x power. And then we'll have z, and finally that last qubit, 0 minus 1 over the square root of 2. And this will be what Alice will have after she applies H to each of the first n qubits of Bob's result C2. This is what C3, this is what Alice will obtain. Now, to finish this problem, the final step will be that Alice measures the first n qubits with the standard basis. And now we just need to understand what is going to happen. Okay, observe that for the first n qubits, we have just the first part of this expression here. This is for the last qubit, the 0 minus 1 over square root of 2, and all the rest of this is for the first n qubits. So we have 1 over 2 to the n sum over x, and I'm not going to go ahead and spell all that out again because I think we understand it. Sum over z negative 1 to the x dot z plus f of x z. Okay? Now, when z, keep in mind now, we're having to sum each one of these sums. The first one is for x, assuming all possible values in the standard basis for n qubit states, and the second one is for z, assuming all possible values. So consider the term obtained when z equals 0, 0, 0, dot, 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 0. In zeros. Okay, so we're picking one term out of this z sum. We're picking just one of those. Okay, this term, this one term, is 1 over 2 to the n sum over x, and then let's think about, and now we don't need the summation for z because we're just talking now about one of the particular z terms, okay? So there's no summation here, we're just looking at one term, and that's when z is equal to this term. Now, think about this. If z is all zeros, then x dot z must be 0, because remember, x dot z is going to be equal to the total number of positions in which x and z both have a 1. But z has no 1s in it, so x dot z is 0, and therefore this would just become negative 1 raised to the f of x power. So we have negative 1 to the f of x power, and then for z we have 0, where that's understood to be actually in zeros now. Now, of course, I want to stress again, there will be 2 to the n different values that z will assume. It will assume this value of 0, and then 1, 2, 3, and again, 1 means n minus 1 zeros and a 1, and then 2 would be 0, 0, 0, 0, all zeros, and then, except for the final 2, we would get 1, 0, and then 3 would be all zeros, and then 1, 1 at the end, and so on. Because z would be represented by a binary number of total length 2 to the n. So we would have 2 to the n different possible values for z, and we have just, from coming out of this sum, and each one, you know, this would, this along with the 1 over 2 to the n would determine the coefficient, but we're zooming in our attention on just one of those terms coming out of the z summation. And so the very first term coming out of the z summation would be this right here, And now let's think about what this is. Okay? Okay, so this will be 1 over 2 to the n. Now, suppose that f of x is constant. And it doesn't matter now whether f of x is constant equal to 0 or f of x is constant equal to 1. Let's just assume that f of x is constant. Okay? Then in that case, all of these coefficients will be the same. They will either all be 1 if f of x is constant equal to 0, or they will all be negative 1 if f of x is constant equal to 1. So we can summarize this in the following way. Okay? So this will be sum over x of 1 times the 0 ket if f of x is always 0. It will be equal to 1 over 2 to the n sum over x of negative 1 times 0 if f of x is always 1. And now what will it be if half the time f of x is equal to 0 and half of the time f of x is equal to 1? Well, for those cases where f of x is equal to 0, we will get positive 1 times the 0 ket. And for those cases where f of x is equal to 1, we will get negative 1 times the 0 ket. And so when we add all of those up, which is of course what we're required to do because this is summation, when we add all of them up, we get 0. So 0 if f of x is balanced. Now let's look at this in still a little more detail. We see that we can say even a little more than this. Remember that here, this summation over x means that we're summing over all of the 2 to the n different values that x can assume. So we will have 2 to the n ones there, and when we sum up 1, 2 to the n times, what do we get? 2 to the n. And so this will be 2 to the n over 2 to the n, which is 1. So we will simply get 0 if f of x is always 0. On the other hand, if we're in this case, then we get negative 1 2 to the n times. And so this would give us negative 0 if f of x is always 1. And we will get 0 if f of x is balanced. And now the key to finishing this all up, remember that what we're talking about here is just one of the terms coming out of the z summation. So, there are 2 to the n minus 1 other terms. So at first, when you look at it that way, it looks like we maybe have not made much progress here. But if you think about it, we've made a great deal of progress for the following reason. We're looking at here the first n qubits of C3. Okay, this is the first n qubits of C3, and then we have this extra qubit down here. And these first n qubits of C3, this is a state. This has been normalized, as we said just a few minutes ago. This has been normalized. Let's maybe go back to the very beginning. Okay, we started out with n zeros. And so we know that this is one of the elements. In fact, this is the very first element of the basis for n qubit states. And so this has a magnitude of 1. And then we operated on that with W. Well, when we operate on that with W is a unitary transformation. So this still has a magnitude of 1. And of course, that first part of C1 is going to go right through, as we talked about, and become the first part of C2. So this right here still has a magnitude of 1. And then when we act on that with W, see, we're just carrying this down. So when we act on that with W, this still has a magnitude of 1. And of course, this is equal to it. So this has a magnitude of 1. And finally, now this right here, all of this. This has a magnitude, we'll need to include this. All of this has a magnitude of 1. And of course, you can see that this has a magnitude of 1. This final bit has a magnitude of 1. But we're not interested in that. We're just looking at this. So these first n qubits have a magnitude of 1. Always. Regardless of what f of x is equal to, these first n qubits have a magnitude of 1. But now we have seen, by looking at just one single term in this summation, by just looking at the first one coming out of the z summation, we see that that very first term coming out will have a magnitude of 1 if f of x is 0, and it will also have a magnitude of 1. This has a magnitude of 1 here if f of x is constant equal to 1. And it will have a magnitude of 0. There will be no contribution at all if f of x is balanced. So what that means is that this whole term here is simply going to be equal to since the very first term has a magnitude of 1, then the rest of the terms are dropping out. The magnitude of the rest of it has to be 0 in these first two cases. So what we conclude then is that these first n qubits will be either 0, will be equivalent to the 0 cat or minus the 0 cat if f of x is a constant function, or it will have absolutely no component along the 0 cat if f of x is balanced. And therefore, if Alice measures, so since the magnitude of this is 1 whenever f of x is constant, and 0 whenever f of x is balanced, we conclude that when Alice measures the first n qubits with the standard basis, she will measure 0 if f of x is constant and something other than 0 if f of x is balanced. So all she has to do is make that measurement, and if she gets 0, the 0 cat, then she knows that, and by 0 I mean all n qubits are 0. If she gets 0, then she knows that f of x is constant. Now, she doesn't know what constant it's equal to. She doesn't know if it's 0 or 1, but that wasn't the goal. She just wants to know if it's constant or balanced. And so if she measures 0, she knows that it must be a constant function. And if she measures anything at all other than 0, she knows that it's a balanced function. And that is how the Deutsch-Jozsa algorithm allows Alice to determine if Bob's function of n Boolean variables is constant or balanced with just one query. So now let's look at some problems for the Deutsch-Jozsa algorithm. And we have 3 problems going with the lecture, and then we'll have at least one in class. But the 3 problems are all related, and each one of these problems I'm going to propose that Alice and Bob adhere exactly to the Deutsch-Jozsa algorithm. They're going to adhere to it exactly, except for a change, one change. And so it says, in each of the problems, tell what Alice will measure if she and I should say she and Bob, if she and Bob use exactly the above algorithm except for the proposed change. So in 33.1, we're going to consider this change, changing C0 to 0. This is n zeros and then 0. You will remember that in the algorithm we discussed in class, C0 is n zeros for the first n qubits and then a 1 for the last qubit. Now we want to consider starting out with C0 equals n zeros and a 0 for the last qubit. If this change, and only this change, were made, if everything else were the same except for this one change, then what would Alice measure when she, in the end, when she measures those first n qubits with the standard basis? Can we say that she will definitely measure 0 if f is constant, and definitely not measure 0 if f is balanced? Can we say Alice will definitely measure 0 if f is constant, and might or might not measure 0 if f is balanced? C, Alice will definitely measure 0 regardless of whether f is constant or balanced. And D, Alice will definitely not measure 0 regardless of whether f is constant or balanced. Which of these situations, which of these is the correct result if we make this change and only that change to the above algorithm? For problems 33.2 and 33.3, those options A, B, C, and D are the same. The only thing that's different is the proposed change. So in 33.2, the proposed change is to make C0 equal to n zeros for the first n qubits, and then plus for the last qubit. And for 33.3, it's we change C0 to n zeros and then minus for the last qubit. So now you'll need a word of caution here is to look at these carefully. I don't think that the answer just jumps right out at you. I think you need to think about it carefully and follow through the algorithm for each one of these cases. And of course, that's the reason I've made up the problem, is to help you follow through the algorithm and understand what it does and when it does it. And so I suggest that you look at these carefully before giving your answer. So those are the three lecture problems, and then we'll have at least one more in class. And that's it. So that's the end of lecture 33, and good luck.